All right, so now we're done with springs. We can move on and talk about pendulums. So I figured I'd pick up at the end of this slide with the spring equation. So we start off where we left off. A little bit more about springs. I talked about this before. They use springs, in a sense, to figure out the mass of astronauts in space because they know the constant K of the spring that's vibrating them. So put the astronaut on the end of it and vibrate them, and you can, using the period, you can calculate the mass. Obviously, they don't just use a giant spring. They have a chair that the astronaut's strapped into. They oscillate, but works the same way. Now, this is just, no big deal. But I want to move on and talk about the pendulum. Now, a pendulum, you have a mass called a bob hanging from the end of a string. And then you pull it off to the side and release it. If you leave it alone, it's going to hang straight down, right? I'm going to pull it off at some angle theta and release it, and it's going to follow, a curved, circular arc like this. The length of the pendulum is L. The mass hanging from the pendulum is M. Now, first of all, notice it's simple harmonic motion, because if you were to put a pen on the bottom of the bob and then let it, pull a piece of paper underneath it, it would trace out a sine wave. So it works as harmonic motion. Now, notice why. That means essentially you need to have an F equals minus Kx situation here. So if we look at the diagram over here, I've pulled the bob out some position, some distance x here, which they didn't label, okay, corresponding to theta up here. Doing a free body diagram, there's a tension force in the string, and there's a gravity force pulling down. Now, that gravity force we can break up into x and y components. The y component exactly cancels out the tension force. The x component pulls it along toward the center. Now, notice a bit of a discrepancy here. X is this way, and the restoring force is at an angle to it. Now, granted, a rather small angle. They exaggerated on here, but at an angle. For true simple harmonic motion, this restoring force should be directly pointing inward like that, and it's not. It's pointing tangent to the circular path, which velocities do. Forces do, and therefore the velocity follows. So pendulums are very, very good approximation of simple harmonic motion. If this angle is very small, sine theta approaches theta as theta approaches 0. So for smaller and smaller angles, sine theta and theta are about the same value. But for large angles, that doesn't hold true. And so if you pull the pendulum out a very, very large angle, this angle becomes very large and it doesn't approximate simple harmonic motion very well at all. In fact, if you pull it up to 90 degrees, the bob will actually free fall for a little bit, and obviously not doing harmonic motion then. It's generally considered theta should be less than 15 degrees. And if you do that, it's a good approximation of simple harmonic motion. You get a good approximation of a sine wave out of the deal. A spring was pretty much perfect simple harmonic motion, assuming no friction or things like that, which we always have to assume. The pendulum is a very close approximation of. And again, we have to assume no friction and whatnot. So without friction, it's going to swing back, forth, back, forth, back, forth forever. With friction up here at the pivot point, eventually it's going to swing to a stop, right? Notice once again that the period is going to be one complete swing. So from starting over here, there and back again is one period. Sometimes people want to say from here to the other side is one period. That's not. That's halfway. You got to come all the way back. So from here, a fourth of the period gets to the bottom. Another fourth gets you to the top on the other side. Another fourth to the bottom again. And the last fourth gets you back. Just like we talked about with springs. Although we'll find a way to calculate that in just a moment. Okay, they talk about what we just talked about. Approximate simple harmonic motion, we talked about that. Now, the equation, it turns out, and you can prove this, and I would have if we'd been actually in the classroom and had time to play around, but we don't. So given what we looked at with the free body diagram and doing some plugging in of formulas and rearranging and algebra and all that, you can prove that the period of oscillation of the spring is 2 pi times the square root of the length over g, 9.81 on Earth. Okay? So once again, notice the longer the pendulum, the greater the period. If you got a short, tiny little pendulum, it's going to swing real fast with a period of much less than a second. You put your pendulum on a really, really long string, and it's going to swing much, much more slowly. Okay? Those old-fashioned grandfather clocks that you may have seen out there, there's a pendulum inside them. And they set it up so the pendulum swings and gets you the timing of exactly 1 second. Okay? But that means in order to make that happen, the length of the pendulum inside's got to be the exact right length to do that. If it's the wrong length, it won't work. When old people went around with those clocks and adjusted the clock, they would literally be adjusting the length of the pendulum by using gears and whatnot to do it. But still, they were adjusting the overall length of the pendulum so that it kept better track of time. The period was much closer to exactly 1 second, or half a second then times 2, whatever they, with gearing ratios they had to do. So the period of the pendulum depends on its length. The period of the pendulum also depends on the gravity of the planet you're on. That makes sense. If I'm on a really high gravity planet, that force mg sine theta is going to be much, much larger, and which is the equivalent of having a stiffer spring. So just like the K for the spring was on the bottom, G, gravity, is what causes the effective restoring force here, and so the bigger gravity, the smaller the period's going to be. In other words, the faster the pendulum's going to swing, because it takes less time. So if you set up a pendulum that swings with exactly 1 second on Earth, you take it to a high gravity planet like Jupiter, it'll swing faster. It'll take less than a second to complete a swing. You take that same pendulum to the moon with lower gravity, and it'll swing much slower. It'll take longer than a second to complete a swing. So in a sense, you can identify what planet you're on by building a pendulum of known length, measuring its period, and calculating g for that planet. Well, at least it gives you some clue what planet you're on. If gravity is consistent with Mars's gravity, then, and it looks like Mars, there you go, right? Now, once again, it's square rooted, so it's not a direct linear relationship, so it was a little more difficult to deal with. Again, if we had lab, we would have actually, if we were there in school doing lab, we would have done this in our lab, actually made measurements of these and figured out that the period relates to the square root by doing some logarithmic graphing. But you guys missed out on all that. I know you're upset. So yeah, easy enough. Notice, by the way, length got to be in meters, and g, of course, in meters per second squared. And if you plug in, play around, it works out to exactly a unit of seconds, which gives you the correct unit for period. So the problems here are really easy. They give you a pendulum length of 0.75 meters. We know gravity. You don't have to be told that. So plug them in. Square root times 2 pi, you get 1.7 seconds as the period of that pendulum. So to swing there and back again, it's going to take 1.7 seconds. Easy, right? Now, notice the period of the pendulum doesn't depend on the mass. Okay, and that's kind of weird. I don't like the way they describe it here at all. Remember, gravity provides a force that varies directly with mass, so it always gives you the same acceleration. So if you put a heavier mass on there, gravity is going to apply a greater force and overcome inertia to the same extent. Okay, so no matter how big or small your mass is, gravity is going to affect it in the same way. Just like if you take a big object and a small object and drop them, they're going to drop at 9.81. It's not going to change. So in the same way, the pendulum's acceleration is not going to change no matter what mass you use either. Okay? So it's no different from what we learned way back that all things accelerate at the same rate due to gravity. I don't like their explanation here. It gets to the same point, but it's not as good. I just don't like it. So a pendulum will swing at the same rate no matter what the mass is. Notice the pendulum swing doesn't depend on the amplitude, as long as you stay within 15 degrees or so. Otherwise, you're going to, it's not going to work as a real pendulum anymore. But as long as you stay with a small amplitude, what amplitude you choose doesn't matter. And in fact, you can see that because in the real world, the amplitude constantly diminishes as friction drags it to a stop. But it swings the same period. Okay, it doesn't slow down as it's coming to a stop. The reason there is if you pull it out at a larger angle, you got a greater restoring force. So it's going to move, it's got more distance to cover, but it's going to accelerate more and therefore move faster. If you use a small amplitude, small angle, it's going to have a smaller distance to travel to get to the other side and back, but there's less acceleration because there's less force. And those values, it turns out, are directly related, and so they cancel out. And so it doesn't matter how fast or how much mass you put on there or what angle you pull it at. All that matters is the length and gravity, which is kind of cool. So that's that. I think I'm going to leave it there. There's more about pendulums that I want to talk about, and this is going to lead us into the concept of resonance. Here's kind of an interesting thing before I let you go. Essentially, your leg is a pendulum. Okay, although notice your leg isn't an infinitely thin string. Well, mine kind of is, but with a mass on the end, the whole leg has some mass to it. And so the length, they show the length of the pendulum from the hip to the foot. In reality, the length of your leg, the pendulum length of your leg, is from your hip to the center of mass of your leg. Maybe in here or whatever. So it will, if you have a real pendulum that's not a massless string, then it's the center of mass that determines the length. And so in reality, this is a way oversimplification here. You would need to find the center of mass of your leg. And then that, from the hip to that center of mass, is the length that determines the swing of your leg. So when you walk, your leg swings as a pendulum and has a period of whatever, which controls your gait, controls how many steps you take and how rapidly you step. If you have smaller legs, your legs swing faster. But of course, they don't go as far, and so you got to take more steps anyway, so it works out. Interestingly, though, if you go to the moon, where gravity is less, even though your leg is the same length, there's a different G now, and that's going to change the period of oscillation of your leg. So you can't just walk on the moon. Your gait is going to be messed up. You're optimized for walking on Earth. You go to the moon and you swing your leg, and it takes forever to get to the end of the swing, and you're already trying to swing the next one, and you're all messed up. So the astronauts on the moon actually worked out a thing where they kind of hopped. Mainly, they also did that because the suits were really, really stiff. Using more modern suits, they may actually end up doing more skipping to try to get a gait that works with the lower gravity, slower swing rate of the pendulum legs. So when they do the moon landings coming up in a few years, at least they say they want to, it'd be interesting to see with the modern spacesuits how the astronauts just naturally fall into a walking rhythm in terms of pendulum motion. So keep that in mind after you graduate and you see moon landings. I think I'll stop there, and we'll talk about resonance tomorrow.